All right, now the moment you've all been waiting for, the second fundamental theorem of calculus. So we've seen that the definite integral of f on the interval a to b was defined using the constant b as the upper limit of integration and x as the variable of integration. However, a slightly different situation may arise in which the variable x is used as the upper limit of integration. To avoid the confusion of x in two different ways, t is temporarily used as the variable of integration. So a definite integral as a number, you have the definite integral from a to b of f of x dx. The definite integral as a function, you do the definite integral from a to x of f of t dt. Because remember, to do a definite integral in general, you take the antiderivative, plug in the upper and lower limit, and subtract. Well, here, the upper limit is considered a variable x. So if you're plugging x into x, that might get a little bit confusing. So we define the function in terms of t, anti-differentiate it with respect to t, and then plug in x in a and subtract. Remember that the definite integral is not a function of its variable of integration. So evaluate the function capital F of x equals the definite integral from 0 to x of 3 minus 3t squared dt at x equals 0, 1/4, 1/2, 3/4, and 1. All right, so you could evaluate 5 different definite integrals, one for each of the given upper limits. But since we're going to define it as a function, it's much simpler to just anti-differentiate, plug in x and 0 and subtract, and get the function that represents the definite integral for those different values, and then plug in 0, 1/4, 1/2, 3/4, and 1 into that. So if I plug in 0, I get 0 because there was no width. If I plug in 1/4, I get 47/64. 1/2, I get 11/8. 3/4, I get 111/64. And f of 1, I get 2. And let me back up a second. What you see here is the graph of our original function, 3 minus 3t squared, graphed over the interval from 0 to 1. As I evaluate my definite integral from 0 to 1, the answer represents the accumulated area under the curve up to that point. So you could see at 1/4, I've only gone up to 1/4 and I've gotten that much area. Now it's not 1/4 of the area because the curve is decreasing and concave down. So as you go across the x-axis, you're accumulating more area, but you're accumulating area at a decreasing rate. Okay, but you could see how the area accumulates as you plug in larger values of x. So you can think of the function f of x as accumulating the area under the curve of f from 0 to whatever you plugged in for x. For 0, the area is 0 because capital F of 0 is 0 and there is no width to our region. For x equals 1, f of 1 equals 2 gives you the accumulated area under the curve on the entire interval 0 to 1. Now this interpretation of an integral as an accumulation function is used in applications of integration. Note that in example 6, the derivative of capital F is the original integrand. So if I have 3x minus x cubed, if I differentiate that, I would get 3 minus 3x squared, which is the same function as the integrand, except just x was in place of t. Now that result is generalized in the following theorem called the second fundamental theorem of calculus, which basically just says if you differentiate an integral with respect to x, remember, the definite integral, as a function, you anti-differentiate it, you get a function of x. If you differentiate it, you should get back to the original function you started with in terms of x. So, if f is continuous on an open interval I containing a, then for every x in the interval, the derivative with respect to x of the definite integral from a to x of f of t dt is just f of x. So that's like we took the antiderivative with respect to t, plugged in x and 0 and subtracted and got 3x minus x cubed. Well, if I took the derivative of that, I would get 3 minus 3x squared, which was the original function I started with, just with x replaced by t. So let's differentiate with respect to x the integral from 0 to x of the square root of t squared plus 1 dt. We have not learned how to anti-differentiate this. But if I took the antiderivative, let me back up 1 second here. If I took the antiderivative, it would be capital F of t evaluated at 0 in x, which means you would have capital F of x minus capital F of 0. Now this is a number, and this is a function. Now if I took the derivative of that, remember I can't actually figure out what the actual function is for the antiderivative, so I'm just using the notation that represents the antiderivative as capital F of x. So if I then take the derivative of that, the derivative of capital F of x, well, capital F of x represents the antiderivative of this function, except I plugged in x for t. So it's going to be like little f of x minus, now capital F of 0 represents the antiderivative evaluated at 0, which would be a number. So if I plugged in 0, I would get a number, and the derivative of a number is just 0. So you would get square root x squared plus 1. Okay? And that's what we got right there. All right, let's do another one. So let's find the derivative of capital F of x equals the integral of t squared dt from 0 to x cubed. Now, using u equals x cubed, you can apply the second fundamental theorem of calculus with the chain rule like this. So capital F prime is df du times du dx. df du is the derivative with respect to u of f of x times the derivative of u with respect to x. So that's the derivative of the integral times the derivative of u. So I'm going to replace the upper limit with u and get u times 3x squared. Now u squared times 3x squared. The 3x squared is the derivative of the x cubed. Now u is x cubed, so it's going to end up being 3x to the 8th. Now that might have been a little bit confusing. Let me show it to you a different way. Remember, now you can get the antiderivative of t squared. I know it's 1/3 t cubed, but for the sake of just implementing the second fundamental theorem of calculus, I'm going to say that the antiderivative of t squared is represented by capital F of t. And I'm going to plug in 0 and x cubed. So that's f of x cubed minus capital F of 0. Now if I take the derivative of that, that would give me f prime of x cubed times 3x squared minus 0. Well, capital F represents the antiderivative of t squared. Well, if I do capital F prime, I'd be taking the derivative of the antiderivative, so I'd be back to t squared, but this represents the t squared with x cubed plugged in. So it's going to be x cubed squared times 3x squared. And if I simplify that, that'd be x to the 6th times, forgot the square there, times 3x squared, which you can simplify to 3x to the 8th. Okay, so I hope that cleared it up a little bit better for you. All right, because the integrand in example 8 is easily integrated, you can verify the derivative as follows. So if you did it this way, you take the antiderivative, plug in x cubed and 0 and subtract, you get x to the 9th over 3. And then if you took the derivative of that, the 9 would come down, the exponent would be 8, the 3 and the 9 would cancel, and you get 3x to the 8th. All right, let me know if you have any questions on that. I know that can be a little bit tricky, so just reach out. All right, see you in the next one.